Okay. Forgive me for drifting away into that, but it is an interesting one. If anybody wants to solve it, do let me know. I'll also like to contribute. And we are actually building our own thing. If anybody wants guidance regarding how to solve it, also do let us know. I'll help you out. Because it's a very fairly interesting problem. All right. If anybody has any questions regarding propagation or summer schools, do let me know. I'll in the next 2 minutes before we start at 7:07, I'll try to answer your questions. Or if you have questions about this particular problem that I stated, ask about that as well in the next 2 minutes before the start. My name is Yash. In every session, I tell you, it's worry searching for internship. We don't have, I mean, email us and we, if there's a role available, the person will let you. Okay, 7:07. I guess there are not a lot of questions regarding anything, including this problem. If anybody wants to solve this problem, do let me know because it's a very tough problem. And a lot of people are trying to solve it using the M25 and LMS. But we should start with today's session because today is going to be an interesting one. I want to know a lot of things from Julius sir. So we should start with today's session. I'll formally introduce Julius sir to all of you, and then we'll start the session. That sounds fine, everybody?
Sure.
All right. So good evening, everybody. I am Yash from Propagation Institute of Space and Technology, and I warmly welcome all of you to session 10 of Propagation Space Month 2026, one of the world's largest student-led space science outreach initiatives. Today, we are delighted to welcome Julius Matthew, sir, an astrophysicist and a galaxy evolution researcher. His research focuses on galaxy formation and evolution, helping us better understand how galaxies have changed over billions of years and what they reveal about the history of our universe. In today's session, titled Galaxies, Their Formation and Evolution, we will explore how galaxies formed after the Big Bang, how they evolved through the cosmic time, the role of dark matter, star formation, galaxy mergers, and the latest discoveries shaping the modern astrophysics world. Julius, sir, thank you so much for joining us today. We are very honored to have you with us. I look forward to learning from you and your valuable insights and research. The stage is all yours now, sir. You can start with the session.
Okay, thank you so much for the warm introduction. And I also first want to acknowledge and appreciate Propagation Institute. This is a very good opportunity that we all are sharing here. So let me quickly share my screen. It's stuck. Okay. Share now. Here I am.
So your voice is, I think we got it. There's a voice problem. We are not able to hear you, sir, properly.
But
Uh, some of your words are coming through, but most of them are not, sir.
I don't know. Maybe it's the internet. I don't know. But my audio is fine.
Yeah, now your words are audible.
Okay. So as I said, I'm a graduate of the University of Nigeria, and a member of all these associations here that I have mentioned. My slides are not moving. What's wrong? Let me try stopping. Where's the third one? Okay. There is something wrong. And then I'm not able to share as I want. So I see
So I think we still have that problem. As soon as you share the screen, that problem comes back.
yeah, I don't know.
Could you rejoin, sir? That might help, or anything like that.
Stop presenting. We try it again.
Now your voice is fine, but as soon as you present, it goes away.
And then as soon as I present, it's a problem.
Yeah.
Okay. My screen should be, and I am audible.
Yeah, I mean, but still it gets cut off sometimes.
Should I just continue, because I think it's now beyond my control, the internet thing.
Yeah. Right, sir. I'll let you know if there is a problem with the voices or anything like that.
Okay, cool. So as long as we've known, we know that we've seen from telescope observations that there are bright spots in the sky that we just term and believe them to be gas and dust. So that is the nebula. Now, a galaxy is coined from two Greek words, gala and kuklos. So the meanings are there. So I would also start with, because I went through the talks and I found a talk regarding hydrogen. So I'll quickly start there. So I've presented here the two hydrogen models. I mean, the Bohr model and the quantum model of hydrogen. So what is interesting here is that it has one proton and one electron, whereas in the other one, it's just bunch of probability. It could be anywhere. So with that said, I'll move
The audio again is gone, sir. Could you do one thing? Could you share us the PPT and I'll try to share it via my Mac, and then you can just speak. I'm not able to hear you, sir, properly, but could you share the PPT to Jitendra, and he'll just send it to me and I'll just share and you can continue.
Okay. Okay. Where
Has it been shared, sir?
Yes, I'm sending it now. I hope the file format will be fine.
What is the format, sir? Because PPTX.
DP.
Okay.
OD. Ubuntu. I've sent it. It's still.
Okay, I think Jito has got it. I'll be sharing it in a couple of minutes after I get the right format. Till then, we apologize, everybody. Just give us a second. All right. There's a network issue. Has it not been sent yet, sir?
It is uploading and it's a bit taking some time.
Right. Uh, I think.
Yeah, it's no. I've sent it.
Okay.
Yeah.
I think we're gonna face a problem, sir, where I will not be able to show the PPTX format because this is a Mac and it does not support that format. I'll have to convert it to PDF. So can we do one thing? Can we make it into a discussion session where you discuss about galaxies and everything, answer a bunch of questions from people, and tell just generally about what it was in the PPT that you wanted to tell, or something like that? Will that work?
Just use my PP.
You can just see I mean, not exactly tell
Sharing
them
screen.
everything in the PPT, but make it into a sort of a discussion session where people are able to ask you a bunch.
Okay. Let me convert it to PDF and send you while I continue with what I'm doing.
Okay. Well, I've got the ODP file. I'll convert it myself, but till then.
So it's fine.
I'm checking if I'm able to open it. Give me a second.
All right. Yeah, it's cool. Yeah, I have converted. I've converted it to PDF. Now there are a few simulations that I have on the PPT, the presentation, so it won't play for sure. So if doing the PDF would work, let me try sharing and see.
Yeah, yes, sure,
Yeah.
sure. Or if people's work date has to be gone and they're fine with the discussion part, then we can do that as you wish. Okay, Joel.
Is it?
Yeah, it's
All right. So let me just use this. I would lose the simulations though, but it's fine. So yeah, there we have it. The picture it's a video though. The picture there, it's actually on a very good night. When you go out, you'd see that patch there. It looks like something was poured. So that's our home. That's our Milky Way. So all this came about in the 20th century when people were speculating that these were just stars, points of light. We always call them stars, but they are not. They are nebula. So a nebula, it's just a collection of gas and dust. So the word galaxy, it's coined from two Greek words. So, and then I went ahead to present us with a quick overview of the hydrogen. Because to be honest, hydrogen is, yes, the most abundant, but then it's, to me, the most useful. So that's why I had to present it this way. So um, here we can see all the elements of the periodic table. But Another question that one can ask is, where do they all come from? And to be honest, most of them come from here. Yes. So the factory of all these elements that we know we use all the days of our lives are from the cosmos. So, which is why I'm introducing of the hydrogen electron with respect. So you would have, let me just go back a bit. You would have the proton here and then the electron, where they would both be spinning in the same direction, either clockwise or anti-clockwise. That is a simplified version. So if both are spinning that way, then the electron goes to either a higher level or a lower level. Then there's a change in spin. So that is what that is. So when that happens, it loses energy at a particular wavelength of 21 centimeters, a photon of 21 centimeters. So where does that hydrogen come from? So we have it in astrophysics that the Big Bang, not necessarily the bang itself. So everything started very small at the singularity, a dense point. And then within the split second, not even up to, it began expanding. So that is the bang. Began expanding, it was cooling at the same time. So after a while, we got the building blocks, which are the quarks, electrons, and so on. But then they could not come together to form an atom. So it took a while. This is a very good summary, not in detail. So it took a while before they recombined, so to say. So it was then that we got this first image, the first snapshot of our own universe. So when one is asking, how do you guys know that it ever was? Well, that was because two astronomers pointed their radio telescopes, well, millimeter around there, the wavelength. So they pointed their telescope and they found that the radiation they were getting was all the same, whether they pointed this way, south, north, wherever. So that is an evidence that that the Big Bang happened. So, and then that recombination where atoms, where we got the atoms now, the electron combining with the proton to form, and then these were mostly what were, in fact, till date, these are what we observe. So the moment they got out of the way, that was when we got this radiation. So these were kind of what were stopping us from getting. So I'll quickly go to stars, because after that, then gravity got to play. So in the whole chaos we had dust, gas, and other things. Then there came gravity. So gravity began pulling on the clouds of gas and dust into to pack them into some dense regions. So these dense regions are where triggered star formation. So these are just nothing more but a molecular cloud. So this is how it happens, just for curiosity's sake. So when you have two hydrogen atoms, so from our basic understanding of force, we know that when they have two masses, they pull on each other. So the net, since it's now a vector, the net direction would now be pointing towards the center. So that is how these regions of high densities were created. So as that happened gradually, hydrogen, two atoms of hydrogen fused. That was what formed stars. So now that we know how they are formed, then we should also have an understanding of, okay, when they are born, how do they live their lives? So we have this summary that they would most of the stars would end their lives on the main sequence, like live their lives on the main sequence, and then drift off as fusion stops, because it will get to a point where it cannot just happen. So that is the difference where we get supergiant, giants, white dwarfs, but I'm not going into in depth in that. So I'll just also introduce some of the building blocks of galaxies. That's why I'm touching everything, kind of. So now, speaking of black hole, yes, it's kind of very difficult to explain, but just look at the black hole as this very simple image I've presented here. So Carl Schwarzschild solved the Einstein's equations and then found this particular radius. So the moment you go into here, then you would have to move faster than the speed of light, which we know it's not possible. So that is what is a black hole in summary. So it's a radii where beyond it, I mean, inward, even light cannot escape. Talk more of you. So that is what a black hole is. And black holes come in different sizes, I mean, mass, right? So we call them black hole masses, and we quantify them by our own sun here, just to make it very simple. So we have the small, the intermediate, and the supermassive black holes, which range from 10 to the power 6 to 10 to the power 10 solar masses. So where do they come from? Okay, so I have presented a brief overview of the Big Bang. Now, there's two possible scenarios where they come from. So it's either a massive cloud of gas and dust would collapse, that is a heavy seed. So that process, the cloud is just collapsing on itself. There is no formation of star. So then the other process can be population 3 stars. Population 3, it's nothing more but the old stars. So we also have the understanding, if at the end of the end life of a star, at the end of its life, it can go supernova. It depends on the mass anyway. It can go supernova, meaning it compresses, it keeps fusing. Remember I said it gets to a point where fusion is no longer possible. So as that fusion is happening, then it goes supernova. Then it leaves behind either one of the three, either. So you can have a neutron star, a very dense star. You can have the black hole itself, yeah, and the other one. So these two are the possible origin of black hole. So one is the so-called light seed, and the other the heavy seed. So surprisingly, my animation is not playing, but I presented it this way to make it easy to understand. Now, anytime one is explaining black hole, dark energy, dark matter, you may not actually convincingly explain it to someone. So anyway, what would have been playing here is just the expansion of the universe. Remember when I explained the origin of the universe? It expanded. So based on observations, we know that the expansion of the universe is slowing down, but just not very recent anyway. Of recent, it has been found that that expansion has stopped decreasing, but rather now it's reaccelerating. So studies have it that dark energy could be the plausible explanation of why it is reaccelerating. So the other plot here you can see they made their simulations with 0.25 of matter, and then dark energy 75.75, so to say 75%. So you can see all studies that have been carried out support existence of dark matter. Sorry, did I say dark matter? I'm ahead of myself now. Dark energy. So you can see most of the points lie on this simulation. So moving on, another content of a galaxy is gas. Very important. Remember, it's gas, dust that come together to form first stars and then subsequently galaxies. So one cannot talk of a galaxy without understanding, okay, its content. So gas is one. So that you can have a neutral hydrogen atom, which is basically then the H we know. Then the ionized one is when it has lost an electron. And then in a molecular state where it's now paired, okay, it has 2 protons and 2 electrons. So dust. Dust is very important. Now, I shouldn't rush to saying how important it is, because, okay, whenever observations are made, the dust content of a galaxy or interstellar medium, it tells us a lot about what the source is. So there are some dust that are known, we know them. It's one of them is carbon, the other silicon, and then the last one that I've highlighted there is PAH. Look, on Earth, we know PAH is just a hydrocarbon. It's just a fancy way of calling hydrocarbon. It's a variant of hydrocarbon, right? So we know PAH to be sort of harmful. So whenever you burn wood or charcoal and it's incomplete, then you would have a PAH. Yes, so it's not healthy, so to say. But yeah, we use PAH, or PAH tell us the star formation in a particular galaxy. So, and then this is actually from one of our study, we can see here that these 2 points. So this is actually around the mid-infrared regions all the way to, yeah. So you can see here that the 2, what is it called? The observed fluxes are not actually in line. What does that mean? This is where the dust comes in. So you expect that whenever you have stars forming in a galaxy, then in the interstellar medium, there would be. So the light from the star would be as the dust would have light from the star and then re-emit it in a longer wavelength. So around this region. So literature has it that let me just be specific on WISE telescope. So the W3, W4, it's usually where the PAH you find it. So whenever the dust absorbs the light, it re-emits it. So that's why pH is a good indicator of, okay, this region is forming star actively. Now moving on to dark matter again, a little movie is not displaying. So this actually shows the existence of dark matter. One may ask, how do you know? So when you plot the velocity of stars of H1 gas, now I'm speaking of this side of the plot, or any, so you should expect a trend from the dynamics, the basic dynamics knowledge that we have. We expect that as you move out, the effect of gravity reduces. Yes, come on. When you make your calculations from the formula I presented earlier, mass 1, mass 2. So as the distance r is increasing, you should expect the force to be reducing. So that is not what is observed. That is the expectation is as you move further, as the radius increases. But what we are observing is you find sort of this trend. So this is actually what is read in astrophysics as the rotation curve. So you find that as you move to larger radiuses or radii, you would see that it's more of, it doesn't change. It's almost flat. So here you can see. So this one was it was plotted to show what we know, and then this is for what is observed. So that is an indication that something keeps the stars from flying off. So when one goes deep into literature, you would find why, or should I say, more evidence of dark matter. Okay, so now since we have picked on all the content of a galaxy, now we can now understand what a galaxy is. So the gravity that a galaxy has, please, I'm not talking about the traditional gravity that we know, but I'm now referring to Einstein, where it's a curvature of space-time. Yes, so it puts together stars and galaxies, and you can see from my definition, I put something there. That means, for me, it's open. Like, we are building more telescopes. So as time goes on, we would add something there. So that is my belief. So if all these are part of a galaxy, I mean, the stars, planet, dark matter, dark energy, you should expect the galaxy to have a mass. Yes. Speaking of mass, I'll keep it and then just dissect the major type of galaxy that we have. They are split in two. We have the normal galaxy and the active galaxy. So what is the difference? Let me just go back a bit to this, my black hole here. So the black hole is a source of gravity that is holding all these stuff together. Now, the moment that particular black hole becomes or begins to accrete surrounding dust, gas, and other matter, then it becomes active. So the black hole is just there, but may not be active. So that is what a normal galaxy is. So an active galaxy, excuse me, an active galaxy is a galaxy where the black hole in the center of the galaxy is actively accreting matter onto itself, whereas normal galaxy it's just there. Nothing really is happening. One can ask, okay, how are you sure that that it would eventually start accreting? We have it from quantum mechanics that it is possible. So now the question, how can a galaxy be? How big can it be? How big can it get? And I left here blank because I believe a galaxy can be as big as it wants. There's no limit, provided it has all the content, all those stuff I mentioned earlier. Now, the ratio, that is what would also span and the sizes of the star and other dynamics. So it can just be as big as it wants. Okay, so since it can be as big as it wants, I've just shown here the progression of how big they are from small, that's dwarf galaxies, all the way to radio galaxies. So a dwarf galaxy, sort of, the name dwarf kind of hints, it's not big. Yes, and then it doesn't come one. It usually has a companion. So if one is asking, is it really possible? Yes. Look, the Milky Way, our home, where we have two dwarf galaxies, the Large Magellanic Cloud and then the Small Magellanic Cloud. So it's one of the smallest that's, I'm talking of the size itself, and then followed by spiral galaxies where as I progress on the talk, I would show you how the spiral galaxy, I think I have it somewhere here. Yeah, that one. So that is how it looks like. And then the lenticular galaxy where it's not really forming stars as a spiral galaxy, but then it has more star forming. It is more star forming than elliptical galaxies. So I've given it off now. Elliptical galaxies basically don't form, they don't have many stars, or should I say their star formation has dropped. Then finally, radio galaxies. Radio galaxy, it's a galaxy where it has jets. Now, I should have mentioned that whenever a black hole is accreting matter and the matter falls into the black hole or on the black hole, right? A stream of jets, the particles are being ejected all the way to parsec or kiloparsec scales. So that is what makes radio galaxies to be so huge. So that is a progression of galaxy sizes. Now, how can the mass be measured? Yes, because we don't just say we can do that. We need to understand how it is done. So light is one of the ways the mass of a galaxy can be measured. So when I say light, I'm not just talking of the visible part of the spectrum, but the complete electromagnetic wave. So, but now for the galaxy, you just need the 21 centimeter line. Remember, I highlighted earlier, the 21 centimeter emission comes from when that single electron in a hydrogen atom, it changes its, it flips its spin, then a photon is emitted at a precise at a precise wavelength of 21 centimeters. So that is one way it can be done. I'm not going to go in depth into how it is done as well. Then another way is a process called gravitational lensing. So look, this is a very simplified gravitational lensing, but the concept of this gravitational lensing we know and see you and use today, it came from Sir Arthur Eddington. So during his time, there was a solar eclipse, and then he wanted to know, because Einstein had already published his work and predicted some of these things, right? I mean, the curvature of space-time and all that. So he was a curious person, just as we all are today. So he waited on the opportunity of a solar eclipse to observe a star that is just behind the sun. I mean, the line of sight. So his adventure was fruitful. He found that the light from the star was bent. I mean, despite the star was behind the sun, he was able to still view it. So that is what gravitational lensing is. So on a large scale, now if you were to replace this diagram of the sun here with a galaxy or a galaxy cluster, please, a galaxy cluster is nothing more but galaxies held together by gravity. Again, gravity is the chief author of everything in the cosmos. So yeah, when you replace the sun with either a galaxy cluster or something very massive, then you are observing, or you want to observe another galaxy beyond the galaxy cluster, for example. Then that is a way you can estimate the mass of that's your galaxy using the curvature of the effect of mass that this larger one has on your line of sight. So now we want to know how far a galaxy is. Yes, when you sit close to someone, you can easily say, okay, this person is 10 foot away from me. And if you're driving to a different city, you can say it's 20 kilometers away from me. Now, galaxies are same. So we always capitalize on light. So again, light is just the full electromagnetic spectrum. So anytime we observe light from a galaxy, we can tell how far it is. So let me just introduce something, a very important, an important concept that is used. So first, let me introduce what is known as a spectrum. So anytime you have a light source and then you have a medium that disperses light, so it could be a prism or a graphene. So it splits the light into its different components. For simplicity, white light, you get this. So we have that understanding that the dispersing medium would split white light into its different components. Now, this brings us to redshift. Whenever you have this spectra, and then you would sometimes see some lines on the spectra. So it's nothing more but absorption lines. So I'm not also going to go in depth into absorption lines, but it's a concept where electrons move from their ground state to a higher energy state or to a lower energy state, and then they either absorb or emit. So, but then the point is, whenever you observe or measure the light from a galaxy, you would find that the lines are moving. So in this case now, it's absorption lines, right? So you would find that the lines are moving towards the red end of the spectrum. So that is what is referred to as redshift. So that word redshift is the most important in estimating how far out a galaxy is. So because when you have an estimation of the redshift from a spectrum, you can in turn use the Hubble law to estimate how far it is. By the way, this is the velocity at which a galaxy can be moving away from you, how fast it's moving away from you. Then the D here is a measure of the distance. And then the H naught here is the parameter. It's a fixed value. So whenever you can use the redshift estimate and then use this relation, and then you get the exact distance. So we don't assume things. So we are sure that this is exactly how far out the galaxy is. So just to build on that, you can see there are different ways you can know how far astronomical sources are, not necessarily galaxies. You see, this is it's an estimation of, okay, how fast is the universe expanding? So several studies have had it that the H naught value changes, which is why in cosmology there's a tension. I'm not into that, but that is a very good way you can estimate how far out a galaxy is. Now, moving on, I would have to touch a bit on star formation indicators. Why? Because the light you get from a galaxy, it's just a summation of the individual things happening inside there. Remember, a galaxy is just something put together by gravity. It's an entity. So the individual stars, the lights from there, it's just a summation. That is what the galaxy light is. So you would have to understand, because, okay, let me say this before I continue. This is actually a spectra, how a spectra looks like. So it is nothing but what amount of light can you measure at a particular wavelength? Yes, that is what it is. And then you can also see from the spectrum here, there are lines everywhere. So let me just start with the ones up. The ones up are the emission lines, the ones that deep down this way, and the absorption lines. Remember when I explained the spectrum, you find black stuff on the color, the spectrum, the color one. Yeah. So these ones are the absorption ones. These ones are the emissions. And then these ones that look pretty stable are the continuum. So that is just what a spectrum looks like. So, or a spectra rather. Now it's now a spectra, not spectrum. It's not one. So how can you know of the indicator that, okay, points, this is star forming? No, this is not star forming. So there are so many things to look out for in the spectra. Let me just highlight a few. Okay, yeah, this one. Okay, yeah, it's here. So when you have H alpha, yes, it's the normal Hydrogen, you know, but now it follows the Balmer series. Yes. So there's other ones are here as well, beta, gamma, and so on. But for star formation indicator, you would mostly look out for H alpha, provided that the redshift is small. Yes, there's a certain limit where you can't use H alpha. So you look out for H alpha, you look out for oxygen 2, oxygen 3. On special cases, you can look out for nitrogen 2. So these are all indicators of star formation. So whenever you get a spectra from the spectra of a galaxy, then you look out for these and then you just can't say, okay, this is it. And then the good part of the spectra is at every particular wavelength, it's unique. A particular element either emits or absorbs. So even if all these things are not here, provided you know where to look out for on the x-axis, you know, okay, this is it. So that is, or those are star formation indicators. Now moving on to morphology and just a touch on classification. This is a very good summary using the popular Hubble's fork or tuning fork. So you can see it's in the shape of a fork. Yes. So morphology, let me just highlight morphology. It's just how a galaxy looks. Yes. And then classification is based on how they look. How do you classify them? How do you put them together? So Hubble did this, and then in his own classification, he made it in sort of a progression. Okay, from those that are not forming stars, those that have little star formation, and those who are giving up stars, burning stars here and there. So it starts, I mean, his classification starts from the ellipticals. So an elliptical galaxy mostly are associated to early type galaxies. So it is good that I am mentioning that now, because we would see as I progress, we would hear rather of early type galaxies and late type galaxies. So early type galaxies are mostly elliptical. So you can see it's just in the shape of an ellipse. And then they have little or no star forming. They don't have dust that, or should I say molecular clouds that support star formation. So the numbers here are just basically how spread out it is. So for 0, it's the way it is. And then you go to higher numbers, then it bulges. You have a bulge. So this particular figure, it's a bit oversimplified because I would expect another galaxy here, which is the lenticulars, which is an intermediate of the elliptical and the spiral. But yes, so as you progress, you would now come onto spiral galaxies. Now, this is an example of one. So it has arms around the nucleus. So you can just see here that it does. And then again, the same applies. For the numbering, it's just a measure of how bulged it is. Then for the letters here, you can see ABC, ABC as well here. So the letters from A progressing upward, it means how stretched out are the arms. So spread out from the nucleus. So this, you can see the A, it's tight, almost tight to the nucleus. And then as you move on, it's open and then open. Yeah, there's a D as well, but it's not here. So then this other side, it's you can see a capital B. So it just signifies barred here. So if a galaxy is barred, meaning it has something here that kind of gives it a good, an enticing look, so to say. Yeah, so it kind of hooks the arms like this, whereas this one doesn't have a bar in the middle. So you can see here, these ones have bars. So where do the bars come from? It's just a variation of dynamics, how the galaxies are, the stars now, how do they move inside the galaxy? So that is one thing that can create the bar. And then, interestingly, our own home, the Milky Way galaxy, it's a barred galaxy. Yes, it has a bar. So you've probably seen artistic impression or oversimplified images of the Milky Way galaxy. You would find the bar at the very middle. Yeah, so that is how galaxies are classified. And then based on their morphology, so you have them there. There are so many classifications, but I would love to touch on the radio-based classification because it happens that I worked on AGN sometime. So I would just have to highlight. Remember, an AGN, it's just a nickname for a black hole that is actively accreting matter. So it is active. So that is an active galactic nuclei. So roughly about 10% of galaxies are active, whereas most of them are just normal, just sitting there. So out of the 10%, you can classify a galaxy, an active galaxy, as being a radio loud or a radio quiet. So remember when the description came of the black hole accreting matter and then emitting stream of jets. So 1 second. Yeah. So the stream of jets are actually sources of radio emission. So an active galaxy is termed as loud in the radio band if the ratio of optical to radio loudness, at 5 gigahertz. If it exceeds 10, then it is radio loud. If it's less than, it's radio quiet. And there are so many other ways of doing it. I happen to work on blazars, which happens to fall on the radio loud classification. And it was blazars and narrow line Cepheid ones, which fall under the radio quiet classification. So here also you can see the radio galaxies. Remember I said the radio galaxy, it's having the jets, but now the jets are not faced towards your line of sight. So it's just like you're looking at it sideways. So that's what the radio galaxy is. So, and then blazars are classified into those that have their radio spectra to be greater than 0.5, then they are known as BLAC or BLAX objects. And then those that are flat, having flat spectra, that is less than 0.5, then you term them as flat spectrum radio quasars. And then we move on to unification. So unification, it's a theoretical proposition that you look at the properties of a galaxy, of the AGN, the active galaxy, and then you just unify it with the line of sight. So So many unifications have been proposed. You can see here, there's the orientation based, where it just says, okay, it depends on how you look at an AGN, at the side or head on at the jet. Look, now here's the jet. Then a distinct between being a blazer, all of them are active galaxies. It distinct between being a blazer, radial quasar, a radio galaxy, a narrow line Cepheid 1, yeah, all the Cepheids. So, and there's a evolutionary base. There's a blazer sequence where it unifies the BLX and flat spectrum radio quasars. So that is what unification is. It's an attempt to simplify how we look at AGNs. So how are galaxies distributed? I've adopted this plot from Yan et al. 2006. So something stands out here, or two things rather. One, you can see red. The other, you can see blue. Well, that is what it is. So early type galaxies, most of them are red, deemed to be red. So since when you plot, I'm now referring to this plot, when you plot the color, that is a subtraction of the color from two different filters, that's the G filter and the R filter, and then you plot it against the absolute magnitude. Here I've simplified what the absolute magnitude is for those joining and us for the first time. So it's just this relation. That is what that's where you get your absolute magnitude. So the absolute magnitude tells you how bright is the source you are looking at. The galaxy. How bright is it from its point of view? So the simplification here is whenever you put or assume the galaxy to be at a distance of 10 parsec, then this is the relation you would use, and then you obtain your absolute magnitude. That means you've eliminated the effects of distance, because if you're just seated in a room, the bulb, you can see it to be bright. Yes, it could be two things. It's either it is truly bright, it is intrinsically bright, or just because you're close to it. So that is why this relation is mostly used. Yeah, so whenever you plot the color against the absolute magnitude, what you will find is most of the galaxies at the top end are red, and then most around less than 0.8, according to this plot, are blue. So remember, I earlier said early type galaxies are red, and mostly late type galaxies are blue. Now, this distinction just clarifies that there's basically little or no star formation in the red, whereas the blue galaxies are just popping up stars here and there. So this is actually where the talk is headed. Now you would have an understanding of the evolution. How do these galaxies evolve? Okay, we know that they are red or blue, right? So when you look at this plot, you would find this shaded region, the green one here. Yes, it's nicknamed the Green Valley. Why? Because we believe that it's a region or it's a phase in the evolutionary cycle where it's two-way, where either a blue galaxy transitions into a red galaxy, or a red galaxy transitions back into being into the blue cloud. So it could be in the red sequence, or it could just be in the blue cloud. But then as it is going to transition, then it transitions into the Green Valley. But now The problem here is the galaxies here are not much. So Pan et al. 2013 has suggested that since they are not much, then the transition must be swift, must be very fast. So that is an understanding of the evolution that we have. So galaxies do evolve, just like you saw with stars. The star, when it's born, it evolves and follows that main sequence. Then maybe towards the end of its life, it deviates to either a red giant, and so on. So that is the evolution of galaxies. Now, moving on, I seriously love the work of Eels in 2018 because he tried to understand the Green Valley galaxies. So what he did was, okay, mostly, remember the color that we're talking of, it's the optical, like the visible part of the spectrum, right? So he decided to go all the way to submillimeter, the longer wavelength. So that's why the plots are like this. So first of all, whenever you plot a color plot, I mean color histogram of galaxies, when you have a bunch of galaxies, something would stand out. You would find the bimodal. You find two modes. So one indicates the red sequence galaxies, and then the other one, the blue cloud galaxies. So the Green Valley galaxies, yes, they are not much, but which is why I love this work by Eels, because he proposed, or they proposed, that there's a Green Mountain. Green Mountain doesn't mean it's replacing Green Valley galaxies, right? But what all it does here is it gives you a better understanding of, okay, when you look at these galaxies in the optical, there's a tendency for dust to obstruct. I mean, when they obstruct, what would eventually happen is they would absorb the light and then re-emit it. Or sometimes they just absorb it and then they just glow. So that glow, you pick it up mostly in the infrared parts all the way to submillimeter part of the spectrum. So that is what he did. And then voila, he plotted this and found the Green Mountain. So the reason why this was observed was because of this Malmquist bias. So there's a tendency for one to always, I'm talking of humans first before I'll go on telescopes. Whenever you you look at a particular region, right? Some things can attract your eyes first, either color or size of something. So it's the same thing as our telescopes. Sorry. So yeah, our telescopes, whenever they look at a particular region in the sky, they have that tendency to be biased to always pick on the brighter ones. So this Malmquist bias is responsible for the Green Mountain that Eels found. Yeah, so which also backs the idea of dust in the galaxies, that they absorb the light. So what are the things that contribute to galaxy evolution? Number one is measure. So we've understood what a galaxy is. So from this image, for example, you see that this is one galaxy, this is another galaxy, but something dramatic is happening. You would see a tail here. By the way, this galaxy is nicknamed the mice, because I think this is the tail, right? So yeah, these two galaxies, as time goes on, that's why it's evolution, right? As time goes on, the galaxy at play in the interstellar medium would bring them together. Not just that, we also have an understanding that galaxies are moving. So there's also a tendency that as they're moving, they would merge. So this is a contributing factor to mergers. So assuming one of the galaxies is a spiral galaxy, which means it has more dust, more molecular cloud to form or born stars. And then the other one, for example, it's an elliptical galaxy. So whenever they merge, they would transfer their properties. So you know that, okay, that other one coming with more dust would merge with this one that is not having dust. So which it would imply a transformation. So it could either now have more dust because of the interactions, because when they merge, the gravity increases and then it attracts more dust and gas from the surrounding onto itself. And then that is what contributes to the evolution of the galaxy, or that is one factor measures. Now, moving on to AGN feedback, it's also a factor. It contributes to how galaxies change. Yes, today you'd view them, maybe after a million years, you'd see that they've changed, something changes, right? So AGN feedback, it's, okay, let me dissect it this way. We know that AGNs, the black hole of AGNs accrete matter and then spit out stuff, either in the jet or wind, because they have winds as well. So if this simulation was playing, you would understand more. But anyway, these things all are spit out in the surrounding. So that is what the feedback is. So, and then there are two types of feedback, the quasar mode and the radio. The radio mode is basically just, it's from the radio jets. And then the quasar, it's from the radiation. So in all, an AGN feedback can either be positive or negative. So it could have a positive impact or a negative impact. So if it's having a positive impact, it means it is actively contributing or adding something to the star formation. So it could be that the shocks from the winds and other things, they could add more dust to it. Whereas if it's negative feedback, then it is taking something away from it. Where that means it's not going to retain its star formation, so to speak. And then this is, excuse me, this is one example, the Galaxy Mercurian 573. So you can see the feedback. These are just radio images. So yeah, we've gone a long way in understanding galaxies. So what are the recent developments, one may ask? And to be honest, everyone was excited when the James Webb Space Telescope was first launched in space. But then we never expected to get some doubts from the observations that would be made. Eventually, using the near infrared camera on the James Webb Telescope, it was found that these guys exist. What are they? The little red dots. Look, I think cosmology has made us understand the relationship between redshift and the size of galaxy, the star formation, and all that. So how can a galaxy be that far away? Because this is seriously redshifted. You can see it from the image here. Its redshift is so high right? Look, we never expected to also observe galaxies beyond a certain redshift. So James Webb said, "Oh, you guys should hold on." And then, yeah, that is one recent or a major recent development. So if you are interested in galaxies, this is where to look out for. You can have data from James Webb and you do your wonderful science. So this is not the end of the talk, but I put it this way so that now I will just share with you some of the results I got from my research, not the one from AGN, the other one from early type galaxies. So we were trying to assess or reassess the quiescence of early type galaxies. And this is work that was funded by the Pan-African and Planetary Space Science Network, and then supervised by my supervisors. And yeah, so I'll just give a brief overview of quiescent galaxies. These are galaxies that are pretty quiet. Why are they quiet? It's just star formation. So it's either they have no ongoing star formation at all, or it has dropped. So, which could mean that molecular cloud is not there that will support star formation normally. So here is how a quiet galaxy would normally look like. Remember, we looked at morphology, and then you can guess quickly that this is an elliptical galaxy, a nicely elliptical galaxy. And then when you are going to look at the spectra now, you would agree with me that when I highlighted the star formation indicators, they are basically absent here, which means that this is quiet. H alpha is not there. You can see nitrogen 2 basically non-existent. Oxygen 2 maybe somewhere there. It's not just it. So yeah, the indicators are just saying, look, there's nothing happening. The dust there is not absorbing anything. That is because there is no short wavelength hitting them so that they can emit. No. So this is how a quiet galaxy looks like. And then I would introduce what a liner is. It's also a type of AGN, by the way. Yes, it is a type of AGN. So to make it short and simple, a liner, I'll just use the spectra now so that it's just easy. SF2 is a galaxy, it's an AGN that you don't look at it, I mean, from the AGN unification, now you look at it the other side. Yes, so this is how a typical SF2 spectra would look like, where you would have oxygen 2 and a little of oxygen 3, or not a little, it's more than the oxygen 2 actually. So look, the only thing that happens in liners is they are very close to SF2 galaxies. So when you just flip this, I mean, the oxygen 3 drops and then the oxygen 2 goes up. That's just what a liner is. Yes. So you can see here that that's exactly what has happened. Yeah. The motivation of our work was from this paper where they looked at early type galaxies, which was, they got it from 2 surveys. I mean, they cross-matched them, SDSS and Galaxies. So in the paper, it's a bit troublesome that, or should I say worrying, that some of the samples, or most of their samples, were not quiet. Yes. So we had to address this, and these are just some that I've highlighted, how we got it. we had to compare the photometry from all of these surveys. We had to perform diagnosis. We had to model the emission from the galaxies using SIGAL. So I would talk a bit on that as I proceed. And then finally, we had to stack the radio images, because the radio emissions from the quiet guys would obviously be not much. So you have to stack them so that you'd see the effect in full. So this is one diagnosis. So it's called the color magnitude diagram. It's a culture in astrophysics where you just subtract the longer wavelength from the shorter wavelength. So this is in the ultraviolet, and then this is in the optical. So you can see the R band it's higher than. So yeah, we did all these diagnoses, and then you can see from the legend here it says still they are quiet galaxies. Yes. However, you find liners that have H alpha emissions, those without, and then AGNs. Yeah, that's a surprise. And then AGNs, very powerful ones that have very broad lines. Yes. So another set of diagnosis was to use the, you could use anyone anyway. There are so many of them. There's BPT, Bradwell, Phillips. So it's just, there are two things you just put on the axis. You just put the emission lines. You could use a, not you could use, there are standards, right? So for this one, you can see it's oxygen 3 against H beta. This x-axis is nitrogen 2 against H alpha. So when you go through literature, you'd find so many of these diagnoses. For this one, it's the equivalent width of the H alpha and then nitrogen 2 against H alpha. So we did that, but we did not produce a plot. We just kept them. Yeah. So let me just introduce SIGAL very briefly. It is used to model galaxies. So you can see here what it stands for: Code Investigation Galaxy Emission. So it has been in existence for quite some time. It is written in Python. So this is how it will look like. It's not GUI. It's not friendly. Like you can't interact with it because it's just something like this. So you would have to specify the model you are using, and then you need to have an idea of the dust, whatever, and the attenuation. Yes, so everything is just kind of specified here. So you would need to read in depth before you make use of this, and then you need to clean your data very well. If not, you're just going to have errors. Yeah, so some results from our models, and one thing stands out. Yes, it also agrees with literature. Look, you can see the ultraviolet part here where it's not just fitting. So this is typical of what has been observed, and it is called the UV upturn. So for some reason, the ultraviolet, I mean the far ultraviolet and near ultraviolet, they just go up. Yeah, the observations you just, and then it's an active area of research. Yes. So with that idea, or with an understanding that whenever you have a dust in your, either in the interstellar medium, you expect it to absorb the light and then re-emit it in this part. So also there's infrared excess. So there's both UV excess and infrared excesses. So this one may not really be like that, but most of our sources because we had to do everything. About 3,417 of them. Most of them were just like that. Yeah, so for the stacking, I'm just presenting for one class. The ones without H alpha. You remember it's here. Yes, the class ones are the liners without H alpha. So this 20 centimeter stacking is at a frequency of 1.4 gigahertz. So it's radio. So as I earlier said, it's radio. These are just radio images that you just stack on each other because they are very faint. So you need to stack them so that you understand, okay, the emission you're getting, is it really significant? Is it much? And you get so many information from that. So I will just conclude with this. Or rather, you can just take this one home. So from our study, there's no correlation between the observed excesses. Remember, I said there was UV excess and infrared excesses from our Seagal model. And then remember the polycyclic aromatic hydrocarbon, the PAH. So W3 from the Ys and the W4, you just find them popping up. So PAH, it's the likely cause of the excesses we observed from the infrared part. And then it is suggested that the the homes, which is referred to as the hot low mass stars, because they are of low mass and then they are hot. They could explain why the spectra of some of our sources were having H alpha emissions. So there are so many possibilities. Could some of these quiet samples be harboring stars such as the extreme horizontal branch, the horizontal branch, the homes, and the post-AGB stars? So because we know, or it is known from literature, that they are capable of ionizing the galaxy itself. So I think that is all from me. Thank you. Stop this because I think it's okay here.
Okay. Okay. Yes, sir. So, sir, my question was about the rotation curve of the galaxies. Why did it drop off when the mass of that galaxy got bigger and bigger?
Okay, yeah, it's a good starting point. So from Kepler's laws, it is expected that as you move farther away from the center of the galaxy, where the gravity is more, then things begin to slow down. I mean, the forces wouldn't be much, so you expect the stars that are that side to sort of be slow. But that is the expectation, right? Now, what is observed is, you see the curve, it goes up and then kind of sustains itself. So it means what is happening at larger distances, I mean at large radius or farther away from the center, is that it is still at the same. It doesn't change. It's not like as you go away, it's the rotation of the stars drop off. No, it's sort of stays the same at all radius. I hope that answers your question.
Yes, sir.
Thank you, sir.
Okay. Good evening, sir. That was a very nice session. Thank you. So my question is, does dark matter play a direct role in transforming star-forming galaxies into quiescent galaxies, or is it driven by some other phenomenon?
Okay, so dark matter itself, should I say, it's an addition because of the models we have. They just basically say, okay, if it's not there, then it's just nothing is going to hold, right? Like keep things together. So for impacting star formation, I would not say it impacts star formation. Yeah.
Okay. Thank you, sir.
Yeah, thank you.
Oh,
Yeah.
yeah. So my video is a bit too bright. I don't know why. Sorry. Um,
Yeah.
so, sir, it was a really nice presentation. Like, I loved how you simplified the concepts and blended them throughout the presentation. So, my question was related to dark matter itself. Like, as I've seen that there are some uh, like bullet cluster, which is 1E0657558. So in this bullet cluster, we have observed that two galaxy clusters collided, and the visible baryonic gas, which should be generating the information gradient, slammed together and they slow down. But like the gravitational lensing map, it shows that the mass center moved ahead, tracking what we call dark matter, or instead of the baryonic gas, that should have been the what should have happened. So do you think this is a proof of dark matter, like this shifting of the gravitational lensing ahead of what it should be?
Well, I would just add, because you've said a lot, I would just add by saying the presence of dark matter just adds to the effect of the gravitational lensing because it's mass, right? So I would say that it is a step ahead. Look, it's a good research that you are embarking on. So it is not conclusive, and that's why in my presentation I was trying to avoid explaining what dark matter, dark energy is because these are concepts that it's
Yeah, it's an
don't just go.
addition. Yeah,
Yeah, yeah. But
I understand.
they are very interesting and exciting for sure. So for one, all we can do is harness all the data we can get, we keep getting from our telescopes, and let's just do the science so that we can prove it beyond reasonable doubt. For that one, I would believe it's a good step. Where you said it has moved and not right. Yeah.
Okay. So my second question is a bit lighter. So, uh, as you said that how big a galaxy can get, you just kept it blank because you think it can get as big as it wants to. So, in that case, would there be a risk of the entire galaxy collapsing under its own mass, under its own gravity?
Okay. So interesting. Now, when you talk of collapse, usually I think collapse happens as a result of like when you look at the quantum side of an atom. But For collapse to happen under such circumstances, it's just going to get big, I believe. For collapse, I don't think it will collapse.
Okay. Thank you, sir.
That's why I kept it.
That
Yeah.
was all. I would like to connect with you on LinkedIn if that's possible, so we can.
Cool. Just
Yeah.
send it and
Thank you. Thank you.
nice. Okay. Let me open the chat and see. The compulsory one, right? Compulsory thing for each and every galaxy. Okay, yeah. So it is a concept that every galaxy should have a black hole. And look, black hole doesn't necessarily mean that it must be at the center of a galaxy. Look, cosmology has also brought to light that there are micro black holes that must have formed during the formation of the universe. So they are just everywhere. Look, and then I would believe that, in fact, even in a galaxy like ours, the Milky Way, it's not necessary to say, okay, you're just having one black hole. But the only compulsion there is to have the black hole at the center. Yeah, for a galaxy, one must expect a black hole at the center. There could be other black holes, like small black holes everywhere, just scattered around. Because, like I said earlier, cosmology has brought to light that microbial black holes, you see microbial, the word is not there, but micro black holes exist. Yeah.
Hello, sir. Thank you for
Hi.
the interesting session. So my question is that how do galaxy mergers and dark matter interact over cosmic time?
Okay. So for galaxy mergers over cosmic time, I think I highlighted two possibilities earlier in my talk. So you could just have, yeah, from Hubble's law that these galaxies are moving and maybe far away, right? So there's a chance that they would uh, cross lines and merge, one, or if they are just in a neighboring, like they are just close, gravity could take a part and then bring them together.
So do they stop star formation?
I mean, you're talking of measures, right?
Yeah.
Yeah, come. Measures influence star formation. Yeah, that is what they do, because when that happens, there's an exchange of material, gas, dust, and so on. So remember, the key thing in star formation is the gas. So the exchange. So gravity, because now they are now one, it has more gravity, and then it's going to attract more stuff from the surrounding, the interstellar medium, and then eventually either shoot up the star formation rate, or if it's just maybe two elliptical galaxies that are merging, you may not really expect the star formation to be much like that. but yeah, it influences star formation.
Okay, sir. Thank you.
Thank you.
Yes, sir. Sir,
Right.
thank you, sir, for the amazing presentation, and have you invested the time to discuss about galaxies with us. It's one of the favorite topics I used to love studying in astrophysics, as I am an astrobiology enthusiast. So I also study some of astrophysics. So, sir, my question is that, sir, I have studied that from somewhere that Andromeda galaxy and Milky Way galaxy is going to be collide. Sir, can you please clarify on this? I know it's very silly one plus, but I'm
No,
curious, so that's why.
it's not silly. It's a very good question. Maybe I should have mentioned in my talk as well. Yes, you are absolutely right. But it's not like it's not now or tomorrow that it's going to merge. But based on studies, they are on a collision course. So um, in some years to come, that is the fate of our Milky Way and Andromeda M31. Yeah.
Okay, sir. Thank you, sir.
Is it true that it's possible to have? I think there are two there, right? It's seen two. Is that is it a statement or a question? It looks like. Oh yeah. So look, even in the lab, right? When I am to make my own measurements and you are to make your own measurements, you'd expect some difference. That's the sigmas. So I would believe that the choice of method, yes, would would affect uh, the outcome of your estimate. It should not be much. That is why we love maths a lot. Whenever you do something, you have a threshold that it should not exceed this, or it should not be less than this. So there's always a limit. I will just add again, that is actually a thing of concern when it came to the measurement of H naught, the cosmological, the expansion rate constant. So that is what has created tension, like because the sigmas now it's up to 5 sigmas. So for that of galaxies, it should not be much. But what can we say if you are to make your measurements and someone somewhere can replicate it and still get that? Then it needs more research. That's how I would leave it as open as that. Yeah. Is it true that it's possible to have universe inside black hole? Oh, yo. That question, I honestly would maybe attribute it to some fiction concepts. Uh, anything that goes into a black hole, not even light can escape. I showed that earlier. So even if you're traveling at the speed of light, you need to travel faster than the speed of light. So for you to have a universe inside of a black hole sounds a bit much, much to take in. So I would say maybe it's not. But yeah, we know we've had the idea of wormholes, right? So it could be. Uh, that's why we research. So we would find out definitely. Okay, so galaxies are born all the time. Look, it's just gravity gets into play and then it brings the stuff together. So there will always be galaxies. It's not going to be finite. One, and secondly, I think there's sort of a misconception about the inflation. I mean, not inflation, the expansion itself. It's not like they are moving, but the space itself is the one moving. So anyway, it sounds abstract, I know, but I hope it's clear. Um, for multiverse, it's a probability as well. So I think I read one paper that was saying one of the patches on the cosmic microwave background, it's an evidence that there could be a multiverse. So found it, but I, I will still leave it as a possibility. Because what are the chances if our model of the Big Bang is correct? It's possible that it happens all the time, like not on a cosmic time scale, but it's possible that it happens. So if it happens, then other universes are born or have existed or are existing. So I'll just leave it at that. But this is yeah, it's a problem that James Webb has brought to us, and we have to embrace it that way. Um, so many of these galaxies have been identified, just like you said, that one. I I would assume based from like on our models don't cannot stand these evidence these observations because it looks like we have to change something. And I would agree with there was someone who was saying that whenever there's something an upset, they would either want to adopt something or yeah. So we would find out. James Webb is barely 10 years, not up to, right? So we'd see how it goes. Okay. So for event horizons, it's just a fancy way of saying things. Remember, I displayed the Schwarzschild radius. So that is just it. Yeah, that is the event horizon itself. So beyond that point, then nothing happens. Our physics break down. That's why it's called a singularity. Um, yeah, I've heard of naked singularity, but it's not. I haven't grasped it as well. Oh boy. Okay, so teleportation. I would also add. I read a paper that it was done, but not with a big whatever. It was done, I think, with, was it a proton, or I'm not even sure if it's a photon. Yeah, so I think it was kind of tested with on in our labs here on Earth. So for teleportation, it's fiction for now till we find out and see. Yeah, because Oh yeah. Yeah, someone is asking if they can get the presentation. I think he got that from I think that it's written somewhere that the laws of physics are the same everywhere, something like that. Yeah. Yeah, it does. Yeah, Galaxies. I believe he's asking of the opportunities in astronomy, right? Oh, yeah. So it's quite straightforward. You can always look up call for applications on the AAS. Let me just AAS job registers. And that is going to be the easier. I'll drop it on the chat so that you can have it. Okay. I should repeat what? Okay. I'm dropping it on the chat. It's there. Uh, job registers, AS job registers. So it depends on your interests. There are so many because sometimes you would find opportunities in galaxies, some cosmology, instrumentation. So if you want to further on the instrumentation, then yeah, you can look up those ones. As well, another great one to do is connect with like-minded persons on LinkedIn. They post these opportunities, so it should be straightforward.
Yeah. Am I audible now?
Yeah, you are.
Yeah. So in the chat, that was the first questions I have raised, and the second questions I'm asked about like uh, if information can never be destroyed, and when it is generated, and black holes are not dead ends but gateway to other regions of space time. Like, could the information that falls into a black hole re-emerge elsewhere in the universe or even in another universe? Like, what happens to the information? Yeah, that's my question. Yeah, sure. Yeah, but like in 1970 or something, Stephen Hawking also showed that black holes emit the thermal radiation due to quantum effects near the horizon. So that is also the things of Hawking radiation, right? But somehow information is generated, right? And it is not destroyed in any other universe. For if I say that atoms are also be there, so if I say that atoms are generated in our body also, so in quantum physics era we can say the atoms has the empty space, but we also had the information, right? If I can tell that this is soul or something else, whatever it is, religious or something, but those are form of information, like those are form of some kind of in qubit also. So there has superposition state that does not appears in our eye, but it appears in quantum era also. So that is true. So that's my question is what happens to the information? Of course, my question is little bit like tricky or kind of imaginary, maybe you can ask, say, but it's really wanna think like I have read lot of research paper in quantum also. So, but I didn't get the answer yet. Yeah, if like black hole sucks the information, so it's not in our universe, right? So if you talk about the mass and energy, so that should have the kinetic energy, the radiation, the momentum. That also depends. So like you have tell that mass and energy here also, so we can also think like the curve space time, we can also think like the kinetic energy, momentum, radiations, and radiation is nothing but the light of that, so that is also be there. So when like in black holes, when an information is sucks or go to that field, it goes, it's like change the mass, it change like kinetic energy to another energy field that we doesn't know about that. So yeah. Yeah, that is the research propaganda, and like scientists are like ruining their time. Yeah, Interstellar also have their own propaganda.
Yeah, I think the concept of black holes is oversimplified. Yeah. Okay. Um, yeah, I liked this one. Highlighting the work of Stephen Hawking. Yeah, that black holes have hairs. Yeah. I cannot see any other question.
Yeah,
Yeah,
I
it's
have
good
lot of
interaction.
questions.
Okay.
Okay, before that, I am also telling you that you are also telling me that black holes, the cosmic vacuum cleaner kind of thing, right? So I seems like this kind of thing, like it is kind of a cosmic vacuum cleaner, and it's easy to enter but impossible to leave. So, what do you think? This propaganda or this eye-catching thing is related to the black hole, or like? Yeah.
Am I audible? I don't know. Yeah,
Yeah,
I've
sir.
had
I
I've had
huh,
okay, go on.
I have one question. Last question. Like, if I talk about the atom, so it's like since atoms are mostly empty space, what fundamentally prevents matter from passing through like other matters?
Okay, I would believe the reason why it's not possible it's because of the electrons. Yeah. So Pauli exclusion principle has said that it cannot occupy more than one energy level. So um, for each atom, it's unique. Like so, if two of, I mean, now you're talking of the concept of coming together. So the two atoms are different. Like, yes, they may be of the same element, but like the energy levels are what I would believe would make it impossible. So I don't know if Yadav
Yeah, but
can add.
in the electron clouds also two objects overlap, right?
Yeah, electron cloud is just like it's discrete. Yes.
Yeah, if you wanna tell me about the Pauli exclusion principle, what I know that Pauli exclusion principle creates an effective pressure that prevents that the atom from occupying the same space. If I'm not wrong,
Yes, it's true. It's true.
and there also has one uh, I can say repulsion also, that electromagnetic repulsion. If you know that, like two objects come closer and electron clouds repel, so that may be the also be the case.
I think I've also read somewhere that, you know, in as much as we feel like we touch things, we don't really touch them. It may sound a bit weird, I know, but it's not like you are really touching it. Yeah.
Yeah, so you just said that Pauli exclusion principle prevent the electron clouds, right?
Yeah, it's not going to allow the electron to occupy the same energy level. That's what I'm saying.
Yeah, the same as the quantum state also.
Yeah, yeah. It has to be discrete.
Yeah, okay. Thank you so much.
Cool. Thank you so much. Okay. Selfie. Oh, sorry. Yeah, sorry. Yeah, I said it's possible. I would believe it's possible because there's a theory that says when you have a white dwarf, uh, it should be stable, we believe. So eventually when a star gets too close and then it's for some reason starts accreting, then it's going to reach that 1.4 times solar mass, and then it goes supernova. And you know what happens when something goes supernova? Then a remnant. You should expect a black hole. That's what I believe. Yeah, it's nice. Yeah. Bye.
Thank you, sir. Bye, sir.